Right, so let's pick up where we left off last time. We said that the wave function psi must be a normalized, well-behaved function. Okay, and by normalized we mean that the integral of psi star psi over all possible locations of the particle must be equal to 1. Okay, so that's why I say it's another word for normalizable is quadratically integrable. Okay. Normalizable simply means that that integral is a finite number. If that number happens to be 1, we say it's normalized. Okay, and so we say that this is this requirement is a consequence of the assumption that we make, known as the Born postulate, that psi star psi is a probability density function. Okay, so the probability of finding the particle should be equal to 1 if you're looking at the probability of finding it anywhere. Okay. Now, we gave an example of how we can normalize a normalizable function. Okay, so we simply multiply it by a constant. Okay, so that the integral of the new function over all possible, the square of the new function over all possible locations is equal to 1. So this is the example we had last time. Let's just go over it again. Integral of psi star f is e tau is equal to 5. So what if that's the case? So we say f is not normalized, but is normalizable. How do we normalize f? We define a new function, which is just f times some constant n. This n right here is what we would call your normalization constant. Okay, so let's make the substitution then for nf in the expression. If g is normalized, then we have to say that g star, integral of g star g d tau must be equal to 1. This means that g is normalized. So you say g is the normalized version of the function f. Okay? So we make that substitution for g right there. So we say integral of nf star times nf d tau is equal to 1. And then we can say that n star, and we can factor out your constants, okay? N star and n, take it out of your integral, times integral of f star f d tau must be equal to 1. But n star times n is just absolute value of n squared. So absolute value of n squared, and I can move this over to the right side. It's 1 over integral of f star f d tau. So we said that this was equal to 5. So what if that was 5? Then we say the normalization constant, absolute value of that is equal to 1 over square. That doesn't mean that n is 1 over square root of 5. It simply means absolute value of n is 1 over square root of 5. If you recall, okay, so n can be 1 over square root of 5. It can be negative 1 over square root of 5 because its absolute value is still 1 over square root of 5. In fact, n can be any complex number that's represented by this circle on the complex plane. Any point on this complex plane that is separated from the origin by a distance of 1 over square root of 5 will have an absolute value of 1 over square root of 5. So in general, n would say 1 over square root of 5 times e to the I 5, where 5 would be an angle from 0 to 2. Okay? So we also said that for a function to be well behaved, okay, not only must be, okay, let's go back here. We said psi must be a well behaved function, and one of the conditions for it to be well behaved is for it to be normalizable. In fact, we want it to be normalized. It also must also be single valued, and it must have a second derivative. Okay, and that condition for the existence of the second derivative has to do with the assumption that we're going to have to make another assumption that we have to make, another postulate, that in that psi is obtained by solving what's known as a Schrodinger equation, which requires that it has a second derivative. So let's look at this next question right here. Which of the functions here is not well behaved for the interval x equals 0 to x equals infinity? So the way to look at that is to just plot it. Okay, so from x equals 0 to infinity, what does e to the negative x look like? Actually, we want to look at e to the negative x and e to the negative x squared. The square, because it has to, we have to see if the square of it has a finite area under the curve. Okay, so e to the negative x, when x is 0, e to the 0 is 1. Right? And what happens to it as x increases? E to the negative x is 1 over e to the x. It's known as exponential decay. 1 over e to the x. So it looks like that. Okay? So that approaches 0 as x approaches infinity. So it's continuous. Okay? And it has the second derivative exists. Its first derivative of e to the negative x is 1. It's going to be e to the negative x times negative 1. Right? The second derivative exists, derivative of negative e to the negative x. So this is negative e to the negative x. dx is equal to e to the negative x. So first derivative and second derivative exist. It's continuous. There's no break in the function. And if you square it, the plot pretty much looks like this. It's very similar. It's still going to have an area under the curve that's finite. Okay, so this is well behaved. And you should be able to show the same thing for e to the negative x squared. Well, what about this one right here, e to the x? Well, e to the x is going to go up like that. So e to the x approaches infinity as x approaches infinity. So that means the square of that will do the same thing. So this is not quadratically integrable. So that function, e to the x, for the interval 0 to x, is not well behaved. Which of these functions is not well behaved for the interval from x equals 0 to x equals 2 pi? What does sine x look like from 0 to 2 pi? Okay, so it's continuous. First derivative, second derivative exists. Is it quadratically integrable? Let's plot, this is sine x. Let's plot sine x squared versus x. 0 to 2 pi. What do you get? You just get the square of that, and the square of that is positive, so you have a finite area under the curve. Okay, so this is well behaved. What about tangent x? Well, you've got two choices here, so that must be the one that's not well behaved. What does tangent x look like? First, from 0 to 2 pi. Tangent 0 is 0. Right? Tangent, if you recall, sine over cosine. So it becomes, hold on. Okay. From 0 to 2 pi, what does it look like? Sine 0, when x is 0, sine is 0, so tangent x is 0. What happens? As you go to pi over 2, 90 degrees, what happens to your tangent function? Cosine becomes 0, right? So pi over 2, this goes to 0, so that approach, if you divide it by 0, you get a very large number, so the function blows up, so it goes to infinity. Okay, beyond pi over 2, over here in the second quadrant, your cosine is negative, your sine starts to go back down to 0, right? So it goes from negative infinity, okay, and it goes back to 0 at pi. So and this one is 3 pi over 2 right here. So you have a discontinuity here at pi over 2. So your function is not continuous in the interval from 0 to 2 pi. So right there and then you can say that it is not a well-behaved function. All right. Now let's apply the Born postulate to these three questions that are coming up. Now let's look at this one. Consider a particle confined to move in a rectangular area shown below. So let's just limit our particle to this area that's marked by this red rectangle. Write down the definite integral that must be equal to 1. What's the integral that must be equal to 1? Integral of sine, absolute value of sine squared d tau must be equal to 1. But this is more specific, so let's be more specific. Exactly what do we mean by d tau here? Well, that means your psi here, if you recall, will have to be a function of x and y, right? So you need to integrate with respect to x, the square of psi, absolute value of psi, from x equals, okay, here's your x-axis, so negative 1, negative 2, 1, 2, 3, 4, 5. So from x equals negative 2 to 5. And after you've done that integration, you integrate the result with respect to y. And integration from for y would go from negative 1, negative 2. So from negative 2 to 0, 1, 2 to positive 2. And so we say that that integral must be equal to 1 if we insist that the particle is somewhere in that rectangle. Okay? Now, just a little bit of a math review about doing multiple integrations. Let's say you have something like a function is equal to, let's say, x squared y. Okay, what would be the integral of f dx from, let's say, x equals 0 to 2, and let's say from y equals 1 to 3? Well, what you do is you substitute your f there, right? And so you would have integral from 1 to 3 dy, and what you have here is, okay, what is that? Integral of x squared y dx, okay, from x equals 0 to 2. Okay, what is that? As far as this integration is concerned, you're integrating with respect to x, so you treat y as a constant, so that factors on the y. What's the integral of x squared dx? That's going to be integral of x to the n dx is just x to the n plus 1 over n plus 1, right? Plus the integration constant, which disappears if you do a definite integral. So this is going to be x cubed over 3, evaluated from 0 to 2. And let's put that in here. So that's going to be y times 2 cubed is 8 over 3 minus y times 0 over 3. Okay? So now that becomes integral from 1 to 3 of, what is this expression right here? That's just 8/3 y dy. 8/3 integral of y dy is just y squared over 2. Okay. Y dy is y squared over 2, evaluated from 1 to 3. So that gives you 8/3 times 3 squared over 2 minus 1 squared. Type to multiple equations. This is the same problem we had earlier. What's the unit for psi squared? Again, you have one particle. So it's going to be a function of x and y and t actually. By the way, that when you said just when we ignored t back here, what we really meant was for a given instant in time, you do this integral, which is just going to be a function of x and y. Okay. So what would be the unit for psi squared in this case? Well, psi squared. Okay. Remember, you're integrating with respect to x and y, right? So that expression right there, psi squared dx dy, must be unitless. Now, what's the unit for dx? The SI unit for that is meters. A length of a unit of length. Dy is in meters. So psi squared must have units of per square meter. Okay? That would be the unit for psi squared. Let's take a look at this question right here. Let's say this time you have two particles confined to move in a rectangular area shown below. Right? The definite integral must be equal to 1. This time we have two particles. So our psi must be a function of x1, y1, x2, y2 times. It has to depend on the coordinates of both particles. So the integral that we have to write would be integral. Okay, let's start up over here. Integral of psi, absolute value of psi squared dx1 from x1 equals, our x goes from -1, -2, 1, 2, 3, 4, 5, 6 to 6. So from -2 to 6. And the result of that, you integrate with respect to y, 1, with respect to the y coordinate of particle 1, and you go from, that's -1, this is -2 right here, 1, 2, 3. So from -2 to +3. And after that integration, you get whatever result you get. You integrate with respect to x2. From x2 equals -2 to 6 again. Okay. And then the result after that, you integrate the result with respect to y2. And integrate from -2 to +3. And this entire expression must be equal to 1 if psi is normalized. Okay? The particle is in the system, the two particles are in this box right here, and this entire integral must be equal to 1. Let's consider two particles confined to move in the rectangular area shown below. It's the same problem as this one right here. Right? Two particles. So what would be the unit for psi squared? Let's look at our psi squared. Okay. That entire integral must be unitless, right? So psi squared times dx1 times dy1 times dx2 times dy2, that entire expression must be unitless. So we have to say that psi squared dx1, dx2, dy1, and dy2 must be unitless. So if that's the case, then these are units of length, so that's meters, that's meters, that's meters, that's meters, that's meters to the 4th next time. So that means your psi squared, the absolute value of psi squared must be meters to the 4th. That would be the unit. Now, how about this one? Let's consider a particle, just one particle, confined to move in the rectangular area with red borders shown below. What would be the definite integral for the probability of finding it just in this blue area shown here? You would expect that to be less than 1, right? Because the probability of finding it in the entire box, the red box, would be 1. But how would you determine the probability of finding it in just that little area there? you would say then, and you just take the integral of psi squared, okay, dx from x equals, let's say, yes, 1, 2, 3, 4, 5. So from x equals 1 to 5, and then you integrate over the y values, okay, and y, you want to go from y equals 1 to 2. And you would expect that number to be less than 1. Why less than 1? Because that's just a small part of the entire range of possibilities where you can find your particle. How about one particle confined to move in a rectangular area shown here? Okay. Okay, actually this is two particles. So psi here is going to be a function of x1, y1, x2, y2, and time. Okay. So for a given instant, what would be the unit, what would be the probability of finding particle 1 in this blue area and then particle number 2 in this green area? So you would say that would be the integral, okay, of psi squared, so value of psi squared, dx1 from x1 equals 1 to 2, and then you integrate the result with respect to y1, and y1 goes from 1 to 2 also. And then when you get the result, you integrate this time with respect to x2 from -1 to +1, and then you integrate with respect to y2 from -1 to +1, so -1. Okay, and again, you would expect that number to be less than 1 because that's not, that's not for certain that you're gonna, if you find 1 here, you'll find particle 1 in the blue box and particle number 2 in the green box. That's not for certain. For certain, but they're both in this entire box, somewhere in the entire box. Okay. Let's take a look at another situation here. This is, what if you have a particle that's confined to move on the circle that's shown below? So this is this segment right here. What's the probability of finding it in that particular segment? Okay. Now, in cases like this, it's more convenient to express psi as a function of theta. You can think of theta as the angle that you make with the x-axis. So if you imagine a line from the origin to a point on the circle, the angle that that line makes with the x-axis, your x-axis is theta. So we're going to integrate from theta 1 to theta 2, and as you can see, theta 1, let's just say that's about 45 degrees. So that's going to be pi over 4, and theta 2 would be 90 degrees. So that's going to be pi over 2. So what's the probability of finding it in that segment of the section of the circle? What you need to do is integrate, okay, psi of theta, which is a function of theta squared, d theta, from theta equals theta 1 to 2. So that would be the probability of finding it with that. Now this is if psi squared is given as probability per radian. Okay. By the way, what would happen if you were to integrate this from all right, let's look at the second case. We'll get back to this. I lost my train of thought there. All right. So that's the case. What if it's per unit length? Well, how is length on the circle, so how is length of the arc related to the angle? What's the circumference of a circle? 2 pi r, right? So if the radius here is r, the length, this length right here is just r times delta theta, right? So this is r times theta 2 minus theta 1. So that means dl, okay? If you're going to integrate with respect to length, dl will just be equal to r times d theta. So the integral would be, in this case, integral of psi squared L from L equals, okay, let's call this L1 to L2. Okay? L1 to L2. Okay? But if psi is a function of theta, you can express dl in terms of theta, so you'd say dl is r d theta. So this is going to be integral of psi squared times r d theta. Okay? So this is what you need if this psi squared is per unit length. Okay, multiplied by the length, that will give you a unitless quantity. D theta is radians, doesn't have a unit there. But since you're changing your unit changing your integration variable from L to theta, you're now going to integrate from theta at L1, which is theta 1, to theta at L2, which is theta 2. So if psi, even though it's given as a function of theta, happens to be given as probability per unit length, then you have to multiply by r before you integrate over theta. If it's given as per radian, then you don't need to multiply by r. Okay? Now, what would happen if psi is constant? If psi is constant? Or psi squared is constant. Then, over the entire circle, can we calculate what absolute value of psi squared is? Well, then you're going to say the integral from 0 to 2 pi of psi squared r d theta must be equal to 1. So what is your psi squared? Absolute value of psi squared times integral of r d theta from 0 to 2 pi must be equal to 1. Okay. So absolute value of psi squared times integral of r d theta. That's just r times integral of d theta is just theta. So r times theta from 0 to 2 pi. So theta evaluated from 0 to 2 pi. So that's just going to be 2 pi minus 0. 2 pi times r is equal to. Note that this is just the circumference. So absolute value of psi squared is just equal to 1 over the circumference, 1 over 2 pi r. It's uniform throughout the circle. Now, this is if psi squared is per unit length. Is per unit length. But if psi squared is per unit radian, then you should be able to show that psi squared is just 1 over 2 pi. Or the absolute value of psi is 1 over square root. That's constant. All right, let's take a look at this one. If psi is a function of r and theta, we can express instead, sometimes it's more convenient to express psi as a function of polar coordinates rather than Cartesian, especially if you're dealing with problem has circular symmetry. So here we're interested in finding the probability of a particle in a circle of radius A. Okay? So in these cases, it would be more convenient to use, instead of x and y, you replace x and y by r and theta. And how do we replace x and y by r and theta? If you recall, if this is your point, x, y, this is going to be your x, this is going to be your y. You can define r as the length of the distance between the point and the origin, and theta is the angle that you make with the x-axis. So you can see that sine theta is opposite over hypotenuse, so y over r. So you can say that y is r sine theta. And cosine theta would just be x over r, adjacent over hypotenuse. So x is just r cosine theta. So how would you write then the probability of finding the particle in a circle of radius A? So you just say integral of psi squared, and so you integrate with respect to theta and r. Do you just say dr d theta? R from 0 to A and theta from 0 to 2 pi. You want the full circle, right? So you go 0 to 2 pi. Go full circle, theta goes from 0 to 2 pi, and from R to A, that's 0 to 2. Will that work? Let's look at psi squared d theta dr. Okay, if this is first unit, remember, this is a two-dimensional problem. This should be per square meter, right? Theta is radians, that's not unit. R is length, so that's meter. So dimensionally, there's something wrong here. That's not quite right. Well, what you need to do is this. Look at the differential element here. You need an area, okay? An area is not, the area, differential unit of area is not equal to d theta times dr. So imagine, okay, let's take a look at the circle here. Two concentric circles right there. So let's imagine that area right there. That difference right there is delta theta, okay? And this difference right here is delta r. Okay? Now, as you make delta theta and delta r very small, so you have d theta dr. Okay? What would be that area right there? Well, what is this length? If that's delta theta, and that length is, remember, is r, okay, r delta theta, right? So if r1 here and r2 are significantly different, then you're going to have to, this length up here and the inner length would be different. But if your dr, if your r2 and r1 are just differ by an infinitesimal amount dr, then you can say that this dl, right, this length right here and this length right here are going to be the same, and they're going to be dl. So you're going to say dl is equal to r d theta. Okay? So length, that length and this length would give you dA. So dA in this particular case would be r d theta, okay, times r. So what we need to do then is we need to integrate psi squared. Okay. First, we integrate it with respect to theta. Okay. Then we multiply the result by r, and then we integrate it with respect to r. 0 to a, and it's going to be from 0 to 2 pi. just rewrite this. You can just say sine squared d theta and then r squared dr over here. Now the order of integration doesn't matter, so you can write it this way also. You can say sine squared times r's, that should just be r, dr from 0 to a, and then whatever the result is, you integrate it over theta from theta equals 0. Now, let's verify that this is in fact correct. What would be the integral of r dr d theta from r equals 0 to a and from theta equals 0 to 2 pi? That would be, let's just separate them. So we put d theta here from 0 to 2 pi, and we have r dr 0 to a. And that should just give you integral of r dr is r squared over 2, evaluated from 0 to a. And then that result, you integrate with respect to theta from theta equals 0 to 2 pi. So what's the integral of r squared over, what's r squared over 2 evaluated from 0 to a? This is just going to be a squared over 2 minus 0 d theta, and go from 0 to 2 pi. So that would be a squared over 2, which I can just factor out, integral of d theta from 0 to 2 pi. And that's just a squared over 2, theta evaluated from 0 to 2 pi. That's just a squared over 2, 2 pi minus 0. That's a squared over 2 times 2 pi. 2 cancels out, and that's just pi. That's just the area of a circle of radius a. Does that make sense? Well, if you add up all of those little areas for all possible thetas and all possible r's, from r equals 0 to r equals a, that just gives you the area of the circle. That's pi. Okay? So this is your integration element of area that you need for the integration if you're using polar coordinates. All right. Now, we do live in a three-dimensional world, so in a lot of cases it's going to be more convenient to use, instead of x, y, and z, to use what are known as spherical polar coordinates, and we're going to go over that next time.